In this problem, we're asked to find the source voltage. We have two transformers. One is a 1 to 10 step up, the other is a 10 to 1 step down transformer. They have a high voltage wire in between them, and we have a load of 2 megawatts with a power factor of 0.85 inductive, with a measured voltage of 2400 volts at a phase angle of 0 degrees. You could think of this as the line and then the load. Before we get started, it's useful if we look back at those rules for the ideal transformer. You recall that the turns ratio, which is the number of turns on the primary over the number of turns on the secondary, is equal to the voltage on the primary over the voltage on the secondary, is also equal to the current in the secondary. Be careful, that's the current in the secondary over the current in the primary. We know the complex power of the primary is equal to the complex power of the secondary. We should also remember this other rule that tells us the impedance of the primary is equal to the turns ratio squared by the impedance of the secondary. Our opening move in this problem is to construct the power triangle for our load. Now we're told it's 2 megawatts, so that goes on the base. We can calculate the angle as the inverse cosine of the power factor. We know it's inductive, so that means our power triangle is pointing up. And then you can calculate the magnitude of the complex power by dividing 2 megawatts by 0.85, which gives us 2.35 megavolt amps. Now that we have the power triangle for the load, we can push it to the other side of transformer 2. We would say that the complex power on the primary of T2 is 2.3 MVA at a phase angle of 31.8 degrees. Since this is a step-down transformer and the ratio is 10 to 1, we can say that the voltage on the primary of T2 is 24 kilovolts. The current, the complex conjugate of the current is 2.35 MVA at an angle of 31.8 degrees divided by 24 kilovolts. Remember that the complex power is the voltage times the complex conjugate of the current. Solving for the current on the primary of T2, we find that it's very close to 98 amps at an angle of negative 31.8 degrees. Now, working our problem right to left, we can go to the secondary of transformer T1 and calculate the voltage. This is an application of Kirchhoff's voltage law. We say that the voltage on the secondary of T1 is equal to the sum of the voltage on the primary of T2 plus the loss in the line. And we calculate the loss in the line as 98 amps at a phase angle of 31.8 degrees multiplied by the impedance of the line. We have to be careful here because there's actually 2 wires in this particular system, so that impedance is 4 plus J20. So the voltage on the secondary of T1 is 24 kilovolts at a phase angle of 0 degrees plus 2 kilovolts at a phase angle of 47 degrees. If we combine that together, it's approximately 25 kilovolts at an angle of 3.3 degrees. Since this is a 1 to 10 step up transformer, we can just do a division by 10, and we can say that the voltage on the primary of T1, which is our source voltage, is 2.5 kilovolts at a phase angle of 3.3 degrees. Before we leave, let's put this into vector notation. On the horizontal, we have our load voltage, which was 2400 volts at a phase angle of 0 degrees. This is our source voltage, which is 2500 volts at a phase angle of 3.3 degrees. And the vector that connects the two is our line loss. And if we were to reflect that line loss across the transformer, we would call it 200 volts at a phase angle of 47 degrees.